Good day from ChemHelp ASAP. In this video, we'll see a very nice example of iodonium ion chemistry. The work in this video was performed by the research group of Professor William Lubell at the University of Montreal. The work was published in the Journal of Organic Chemistry. The citation is on the following slides as well as in the video description. At the top of the screen is a single reaction selected from the paper. We'll get to the structures at the bottom in a bit. The alkene in this 9-membered ring reacts with iodine in THF to give the product shown to the right. This type of reaction is called a transannular cyclisation because a new ring is formed, the cyclization, across an existing ring, transannular. Under these conditions, we would expect an iodonium ion to form. Since the iodine in the product is up, I'm going to assume that the iodonium ion forms on the top face of the alkene. I'll propose perhaps the simplest mechanism that can explain the product, but there are multiple possible pathways. Here is a possible mechanism for the formation of the iodonium ion, which is drawn in the lower left. Iodonium ions are easily opened by nucleophiles. Amide nitrogens are poor nucleophiles, but the proximity of this iodonium ion likely helps the reaction to occur. If we attack with the nitrogen lone pair, we'll simultaneously open the iodonium ion and form the second ring in the product. That gives the intermediate in the lower right with a positive nitrogen. The methoxy groups on the benzyl chain are perfectly positioned to break the CN bond and neutralize the nitrogen. That gets us to the final product. A comment on stereochemistry. I find going from the stereochemistry of the iodonium ion to the bicyclic ring to be difficult. In the far upper right is a piece of the molecule with the iodonium ion. The nitrogen opens the iodonium in an anti-fashion. Here is the open product. Note that the hydrogen is up. Let's rotate about this CC bond to get the same backbone orientation as our product. So on the product in the upper right, we have this zigzag orientation. When we do the rotation, or stereochemistry on the left, is unchanged, but the orientation of the groups on the right stereocenter now place the hydrogen down. This is just like the bridgehead H in our product, which is down. The Lubell group used this transannular cyclisation to prepare a number of different structures that are slightly different in terms of the skeleton and stereochemistry. Molecules like these can be incorporated into proteins. So the protein backbone, here's our N-terminus, passes through the small molecule onto the C-terminus. These molecules, small molecules, force the protein into a turn, which is called a beta turn. This is a protein conformation. These molecules are tools that influence protein conformations, build disease understanding, and can assist in drug discovery. In conclusion, the Lubell group used iodination chemistry to perform transannular cyclizations in the synthesis of beta turn mimetics. If you want to see more details about this chemistry, then check out the reference on this slide or in the video description. The description also contains a link to the Lubell Research website. Please subscribe, like, or leave a comment. Take care.